All right, folks. Well, welcome back. Hopefully, you were able to watch the video yesterday afternoon and try to make sense of that. We went over a little bit more the how we can interpret these photoelectron spectrum and what we can do with these peaks here and what information we can obtain from these peaks here. Okay? And so please make sure you watch those. What I'd like to do today is to finish up with the this morning is I want to finish up with the discussion, go over photoelectron spectroscopy, go over a few more examples of spectra that you may see on the AP exam, and that will give you more practice with interpreting the spectra, because you got to be able to interpret the spectra, folks, and that's going to be the important part. And so we'll finish up with that, and then I would like to start then with Beer's law, which is another spectroscopic technique using visible light. And so we'll talk about that today, and then I'll wrap that up tomorrow for one of the weekend lectures, and then I'll start chapter 10 over the weekend. I'm sorry, the afternoon session today. We'll finish up with Beer's law, and my hope is that we can get started with chapter 10 and wrap things up over the weekend. Okay, and that way then Monday, hopefully, we'll just I'll wrap things up for you and see if you have any questions. Come by after school, and then I think the exam is the Wednesday, the 11th. Okay, so make sure then that you are still prepping. I know I've been answering a few emails from a few of you. Do your best with it, and like I said, try. You have nothing to lose. Like I pointed out earlier, from what I understand, the grading for the AP exam this year is going to be a lot simpler. I think they'll be a lot more lenient with what they will do, and so of any year, this may be the best year to take the AP exam and get a 3, 4, or 5. Okay, so let's go ahead. So let's go ahead then. Let's finish covering the material that you will need in order to have the information to help you with the AP exam. Okay. All right. So photoelectron spectrum comprises of peaks, folks, and on the spectrum itself, it's labeled with the relative number of electrons, or the amount of electrons listed along the y-axis, and the binding energy listed along the x-axis. Sorry. Typically, what you will see then is that you're going to see then that the low end, the lowest energy is going to be towards the right, highest energy towards the left. And so we call this upfield here. So if peaks are upfield, they have more energy, meaning then, remember, more energy, more binding energy, meaning that they are, it takes more energy to remove them from the electron. That means their ionization energy is going to be greater. So the further upfield these peaks are, the closer they are to the nucleus, the stronger they are bound to the nucleus. Okay? The further downfield they are, that means then that they are further away from the nucleus, meaning they require less energy to remove them. Okay, so the position of the peaks on the x-axis, allows us then to determine the position of the equivalent electrons relative to the nucleus. Okay, so make sure you keep that in mind. So with that said, then the only other information you need to obtain from the photoelectron spectrum here is the size of the peaks. Okay, the size of the peaks then indicates the relative amount of electrons that's represented by that peak. Okay? All right, so that's what we have here. We were able to interpret spectra. We did a few examples where we were able to take the spectra of a single atom and then locate all the electrons of a single atom there and use that data to support the electron configurations that we came up with. Okay? What we left off with yesterday afternoon was that we were talking about looking at a photoelectron spectrum where you overlay two different atoms here. And so if you notice here, we have represented by this peak here a single hydrogen, and by this peak here helium. Okay, so we have then the electrons for helium, and let's go ahead and write. And so we left off here by talking about then. Okay, we saw then that when we identify these electrons here, okay, we expect then that the peak that represents helium here should be twice as large as the peak that represents hydrogen. Why? It has two more hydrogens than two more electrons than hydrogen. Okay, so that's why we have the relative size of the peak, the difference here in the size of the peak for the 2 electrons for helium versus the 1 electron for hydrogen. So that I think makes pretty good sense. Okay, and so I've drawn for you here the electron, just a really rough Bohr diagram for helium and for hydrogen. So you have then the 1 electron for hydrogen here and the 2 electrons for helium over here. Okay. So I think that was pretty straightforward. What I wanted to get across to you and what you needed to understand towards the end of the lecture yesterday is why then are these two electrons, if the position of the electron of the peak supposed to represent then how far the electrons are from the nucleus, if we notice then this electron here, this electron from hydrogen, and these two electrons from helium, they're both in the 1s orbital. They're both in the orbital in the ground state. They're in the orbitals that are closest to the nucleus. Why then is the helium peak here shifted upfield, meaning then that this peak here represents more energy, that it took more energy to remove this electron than it did to remove this electron. It took more energy to remove these two electrons than it did to remove that one electron. The question is, why was that? Okay. Well, it comes back to then, remember, when we talk about binding energy and thus the ionization energy needed to remove the electron, okay, it depends on the attraction. How strongly are these electrons attracted to the nucleus? Okay? And so if you take a look at this here, and I apologize, yesterday I gave you the wrong equation for Coulomb's law here. This should not be squared here. So it's going to be Coulomb's constant, charge 1, charge 2 over the radius, how far the charges are away from one another. Okay. All right. So with that said, then, if we take a look at this value for hydrogen, I'm sorry, okay, K doesn't change, but what we have here is the proton, the attraction then is between a +1 and a -1 charge, and then the distance there would be the Bohr radius. Okay? And we would expect, we're going to hold off on that for a minute because we can explain this shift to right here just based on the interactions here. Okay? So let's go ahead and take a look at the energy for the helium. Okay? K is a constant. Okay? This time, though, you have 2 positives and 2 negatives. The very magnitude of the charges themselves is twice as large here. Okay, and so if you notice here, I mean, I wouldn't correlate it directly here, but you do notice then that the binding energy here is almost twice as large as the binding energy for the hydrogen here. That is how we can explain why there is a shift in the helium peak here upfield as compared to the hydrogen, even though all of the electrons are in the 1s orbital. Okay, and so what we can say then is, if we're looking at a single atom, if we're looking at the electrons within a single atom, yes, the shifts in the peaks then would represent the relative locations of those electrons. However, when we are comparing different atoms and we're comparing the location of the electrons in these different atoms, we have to, first of all, determine where the electrons are located relative to the nucleus, and then what the charge is. Okay. And so we could argue then that yes, these electrons here get pulled or not, it's not pulled in as much, so it will be further out as well. Okay, so making this this a little bit larger, which makes the binding energy here also smaller. Okay, but essentially what we have here then is what we're saying then is that this electron here from hydrogen is not held in as tightly as these 2 electrons here are from helium. I hope everyone is clear on that now. Okay. One interesting question that I haven't yet seen asked, but I think that the question should be asked. I feel like it will be asked any day now. Okay, and that is, once you remove this 1 electron here, okay, once you remove that 1 electron, what's true about the energy of this remaining electron here? So let's say then we have the helium plus atom. Would it be easier or would it be harder to remove this 1 electron here? Okay. Well, obviously the answer would be, it would be much harder. The ionization energy to remove the 1 remaining electron here would be much harder, which means then, for a couple things, if we were to compare the peaks for helium versus the helium cation, okay, we would expect then that the helium cation's 1 remaining electron should be shifted downfield. And if you can imagine this, if we were to draw that in, we can imagine then that it would look something like this here. Okay, where it'd be 1 electron, helium cation would be 1 electron. Okay, so it'd be half as large as that one, but it would be shifted down. It would be shifted even further upfield. And the reason then for that is that if you can imagine this, Now that you have this one electron here, okay, it's going to be pulled in much more, it's going to be attracted much more tightly to the 2p here. And furthermore, and this is what we talked about, we back in chapter 8, we lose the repulsion energy. Okay, there's a certain amount of repulsive energy here that repels these two, that kind of pushes them apart. You lose this one electron here to form He plus, and with that, when that's gone, you would have this one electron being pulled in even further because you've lost that repulsive energy. Okay, and so make sure you keep that in mind then, that if we had this He plus, if we had a helium cation, you can imagine that that one electron here, that one remaining electron, the peak that represents that one remaining electron would be shifted further upfield, representing more energy, because you're losing that repulsion. There is repulsion here that kind of helps, if you want to think about it, kind of helps push one of these out. Okay? Because so you got the attraction between the electrons and the protons, but these electrons are also repelling each other, which means then one, they're trying to push each other out. Okay, so they're trying, that repulsive energy will help lower the binding energy, the ionization energy here for the two electrons here. Okay. All right, so with that said, please make sure you're able to account then for all these peaks, and there are different reasons that we see these shifts in these peaks, upfield or downfield. We have then attractive and repulsive forces you have to account for as well. Please make sure you practice that. The homework for tonight that I've assigned for you is more practice in reading spectra, and make sure you're able to do that, okay? All right, very good, folks. And so let's continue on then. Let me clear this out here, and let's take a look at another one, okay? Let's just practice this more. Like I said, let's practice more spectra here. All right, so I give you a spectrum here. Okay, I give you a spectrum here, and this spectrum represents one of these four atoms. Okay, the spectrum here represents one of these four atoms. I would like you to take a couple of minutes here, just a couple of minutes, to try your best with this. Which one of these? So this is just this spectrum here represents one atom. Okay, we're not overlaying any different atoms here. So does this spectrum represent lithium, boron, nitrogen, or neon? On your paper, what I'd like you to do then is identify what atom is represented by this spectrum here, and then label it. Label the peaks. Okay, label the peaks. That way, then I know that you are going to be aware of which one this is. Okay, so go ahead and take a couple minutes to get that done, and then let's take a look at it. Okay. All right, let's go ahead and let's take a look at this, folks. Okay? What I'd like you to do then is, first of all, if we're saying that this is one atom here, we have then three unique peaks. Okay, we have a peak here, which represents a unique set of electrons. Remember, the different peaks on a spectrum represents unique electrons. That means electrons in different locations. Okay, so you have electrons here, you have another set of unique electrons here, and you have a third set of unique electrons. That means you have electrons located in three unique locations in the atom, around the atom itself. Okay, so that already should really help you figure out what to do here then. So what I would do next then is, let's go ahead and write out the electron configurations. We know what these are, okay? Let's write out the electron configurations for each one of these atoms here. So we have lithium, we were told that we have boron, okay, nitrogen, and neon, okay? All right, let's write out the electron configurations for these here. So we're kind of working backwards here, folks. So we have then 1s2, 2s1. Okay, for boron, then it's going to be 1s2, 2s2, 2p1. Okay, for nitrogen, then we have 1s2, 2s2, 2p3. And then for neon, then we'd have 1s2, 2s2, 2p6. Okay. All right, so let's go ahead then. Let's consider what we have here. We've already said then that there are three unique peaks. Okay, three unique peaks, meaning that there are three different types of electrons. Different. When we say different, that means then electrons located in three different places. Okay. Let's take a look at the lithium electron here, lithium electrons here. We have lithium, we have electrons located in the 1s orbital, and we have and a single electron located in the 2s orbital. So we have here for lithium two unique locations. Here we have a spectrum that indicates there are three unique locations for these electrons. So therefore, this cannot, based on that alone, this cannot be the the spectrum for lithium. Okay. All right, so that leaves then boron, nitrogen, and neon. Boron, nitrogen, and neon each have, so we have 1, 2, 3 unique electrons here, same thing here, 1, 2, 3 unique electrons, and all 3 of these then have 3 unique electrons. However, folks, on the AP exam, hopefully you can see that you can eliminate lithium right away just simply by looking at the fact that you only have 2 unique types of electrons, 2 types of electrons. Okay? So now the question is, which one of these 3 then represents this spectra here, is represented by this spectra here, okay? All right, so let's now compare then the electrons here. So we have then these electrons here, whatever these electrons here are shifted furthest upfield, they are shifted furthest upfield, which means then, folks, this must be the 1s electron. Okay? That means that whatever this atom is represented by this particular spectrum here has electrons in the 1s orbital. Okay? The next one up then is going to be, the next one downfield then is going to be this peak here, which probably represents then the 2s electrons in the 2s orbital, and this must represent the electrons in the 2p orbital. So make sure you're able to identify then the locations of these peaks. Okay, so depending on where these peaks are on the spectrum itself, we now can identify where these electrons are located. So the electrons represented by this peak here are going to be in the 1s orbital. They are furthest upfield, greatest in energy, closest to the nucleus, and therefore you have the 1s orbital closest to the nucleus. This represents then going up, going downfield here. We have then, that means we're moving further away from the nucleus. The next orbital over is going to be the 2s and then the 2p. Okay. All right. So that doesn't help us very much because boron, nitrogen, neon all have electrons in the 1s, 2s, and the 2p. Now it comes down to the relative height of these electrons, of these peaks here. Okay, so let's go ahead and examine what we have here. Okay, so if you notice here, the height of this peak and the height of this peak are exactly equal. Okay, which then we can assume then would represent the 2 electrons in the 2s orbital here and the 2 electrons in the 2p or 2s orbital here. So therefore they're equal in height, which means then that's what we have right here. So again, that doesn't help us differentiate between boron, nitrogen, and neon. Okay, the 2p electrons. Let's go ahead and take a look at the 2p electrons now. Okay, all right. Let's say then, let's just say then, if this spectrum is supposed to represent boron, okay, each one of these peaks represents 2 electrons. If you look at boron, boron has only 1 electron in the 2p orbital. So you can imagine if this peak were for boron, the peak then would have in the 2p, the 2p peak then would only be half as big, half as large as these 2, because that would represent then 1 electron. Okay, so this graph here, this peak here is not half of these 2, and hopefully you see this. You only have 1 electron in the p orbital here. If each one of these here, each one of these peaks represents two electrons, the last peak here for boron, if this were boron here, it would be somewhere here, the 2p1. Okay, this would be for boron, 2p1. This peak here would be half of these, and if you notice, it's not. So therefore, this spectrum is not for boron. So we've eliminated boron, we've eliminated lithium already, okay? Which leaves us then nitrogen and neon, okay? All right, let's take a look at neon before we come back to nitrogen here, okay? Neon here has 6 electrons in the 2p orbital, okay? So if it's 6 electrons, you can imagine then whatever the peak is, then it's gonna be 3 times larger than that. 3 times larger than that, which means that it would be, let's say here, that's 1, 2, you got 3 times 1, you got 1, 2, and it would be off the graph right now. It would be 3 times as large. You can imagine it would be somewhere up there, somewhere up there. Okay, so that would be the peak. Sorry, let me go ahead and redo this here, folks. Okay, the peak for the 6 electrons then would be somewhere way up there. The peak then would have to be, so this would be half of what this peak is. This would be 6 times what this peak is. And obviously this is not 6 times larger, okay? This is not 6 times larger. If you notice, if there's anything else, it's only about 1 time, let's see, 1 1/3 times larger than, I'm sorry, 2/3 times larger than what this is right here, okay? And so with that said, then we can eliminate neon, okay? And so this is the spectra then for nitrogen. Okay, this would be the spectrum for nitrogen. I would be curious, and I would ask you to do this here. Okay, on this graph here, could you, and your homework for tonight's going to ask you to do this. Okay, can you draw the graph, the spectrum for that? Okay, could you draw the spectrum for that? Now that you have this here, could you draw the spectrum for the remaining three? Okay. Now I haven't. I've yet to see them ask you this question on the AP exam, but be able to do that, because if you can do that, you really have an understanding of this spectrum. Okay. All right. Very good, folks. So let's go ahead then, and let's continue on. Okay, let me take a couple more minutes to go over a little bit of time here. Okay, and let me ask you to do number 10 here in your problem set. What I'd like you to do here is do number 10 in your problem set. Okay, and then what I will we'll do this afternoon for the afternoon session is that we'll finish going over this spectrum. I'm okay with spending this time on the spectrum because it's important that you know this. And then what we'll do is I'll quickly go through the remaining set of problems. So please do number 10 here on your paper. And submit that as well for the lecture today. Okay, and then this afternoon, when we continue the discussion in the afternoon here, I'll work out this problem for you, and I'll work out the remaining three. We have your two spectra. We have two more, three more spectra that we'll work through, and then we'll start on to Beer's law. And so Beer's law is fairly quick. We can go through that fairly quickly. I think many of you will be familiar with Beer's law from your bio classes, and so hopefully you remember that. But if not, then I'll introduce that to you, and that'll be will be done with the two different spectroscopic techniques that you need to know for the AP exam and that you need to know for our class. Okay. All right, folks, very good. So let's go ahead and finish up number 10 and then submit it, and then I will see you this afternoon. Okay. Have a good morning.